So this work is about delta compression for mobile file system. Yeah. I'm Lipin from NYCU Taiwan. So mobile applications, they are becoming more and more intensive. So on the left-hand side, you can see the I/O structure of Android systems. Okay, so the applications, they generate a lot of write I/O requests to the mobile storage, and we know that the mobile storage is based on flash memory, and flash memory has a limited lifetime. That means it can endure only a limited cycle count of program and erase cycle. Okay. So that brings a serious concern about the flash lifespan. And the problem is getting worse. On your right-hand side, it shows that manufacturers, they are trying to migrate to high-density flash memory. Okay. So for example, here I show TLC and the QLC here. And for QLC, the P cycle count limit is just 1,000. Okay. So if we combine the two factors, this is really a serious concern about the flash lifespan. Okay. So the motivation of this work is we are thinking about transparent write stress reduction. Okay. So if we can do that, that could be a win-win because mobile applications, they can continue to be write intensive. But the manufacturers, they could be highly confident to switch their flash storage to higher density, cheaper and larger, such as QLC. Okay, that is the motivation of this work. So based on this, let us look at the mobile file system, F2FS. So it is basically a log structure file system. And we are in particular interested in the inode structure as shown here, okay? So as you can see, there is an inline area in the inode, okay? And this area occupies a very large proportion of the inode space, as you can see here. But according to our analysis, this area is often underutilized, and there are many free space, much free space here. So our approach is on delta compression. So our basic idea is to utilize this unused area to store the tiny delta here to reduce the write stress. Okay. So before I introduce our method, let us review existing method for write stress reduction for F2FS. So the first method is inline files. Okay. So if the file is small enough, then we can directly store the data into the inline area of an inode. So by this way, we can combine an inode and data block. We can combine the two into one single file inode, okay, to reduce the write count. But the problem here is only a small number of files are qualified for this optimization, okay? And for the second method, that is, of course, we can use regular data compression on F2FS. So here we show 5 blocks, and they are compressed and packed into one single block, okay? So we can reduce the write I/O count. But the problem here is data compression, not delta yet, okay? Data compression, regular data compression. Its compression ratio depends on the data pattern. Okay, so oftentimes the compression ratio is not good. Okay, that limits the usefulness of compression. Compression also increases the system design complexity and increase the I/O overhead for render read and render write. Okay. So now we analyze the mobile I/O workload, and yeah, based on this result, we have a few observations. The first is about 90% of all files, they do not use all the pointers in the inline area. Okay, that means these files have some free space in their inline area. Okay, and the second observation is about 80% of all writes are updated. And the third observation is pretty important, that these updates they only have small changes to the existing content. Okay, the delta are tiny, as you can see the number here. Okay, so so we are thinking that delta compression might be a good way to go. Okay, we further analyzed the file type of I/O writes, and we found that SQLite and the temporary files, they contribute to the majority of I/O writes, and they are the source of tiny updates. On the right-hand side, we further observe the inline area usage. Here, to our surprise, about more than 90% of the inline area is unused. Okay, that means the file only have a 1 or 2 pointer to data block. Okay, and then we also found that inode in the patch catch, it catch really well. That means we can append multiple small delta to the inline area before the inode is actually flushed to storage. So, okay, so this figure shows the architecture of our proposal, and basically it is based on F2FS, but we include the two major components, DCI and the DCM. DCI is delta inlining. So when we generate a block write, DCI first check if it is an update. If it is an update, so DCI also check how large is the delta. Okay, if the delta is small, then DCI insert the delta into the inline area of the inode. Okay, but because the inode size is still limited, okay, so it is possible that the inline area overflow. So in this case, selected delta will be evicted from the inline area, and the evicted delta will be handled by DCM. DCM will store the evicted delta using delta blocks, regular blocks. Okay, that is overall architecture of our approach. So this shows how DCI works. So on update, DCI first compare the base original data with incoming data to produce the delta. So the comparison is based on XOR. So as shown in this example, because the change is small, the XOR result contains a lot of 0 here. So we can use lightweight encoding, such as run length encoding or LZO, to transfer, to convert the delta into a very small unit, and then embed the small delta to the inline area of the inode. Okay, that is how DCI works, basically. Let me emphasize that because this is delta compression, so For regular delta compression, it is possible that we have a delta on delta and on delta and on delta. Okay, so that will increase the real overhead. But in this work, we limit the largest number that a base block can have to 1. Okay, only 1 delta. That means on every update, we create a new delta to replace the old one. So as I mentioned earlier, the inline area, the size is still limited. So how about when the inline area overflow? So basically, we will do delta replacement here. So there are several cases to consider. The first is if the file is growing, then that means we add new pointer here. Okay. But if the inline area becomes full, we replace existing deltas here in a first in, first out manner. Okay? And there are other cases we are doing update. Okay? So there are, actually there are some details here. You can check the papers of that. But the concept here is if we replace an existing delta here, if the replacement gives us a better long-term I/O efficiency, then we do it. Okay, that is a basic principle here. So on replacement and selected delta will be evicted from the inline area, and the evicted delta will be handled by DCM. So now let me briefly explain how DCM works. So DCM accepts the evicted delta. Basically, DCM store delta in regular block, just as we store data in blocks. Okay, it uses meta page, meta block, and the compact block here to store the evicted delta. But one thing I want to mention is DCM only handles read code, write hard file. Why is that? Because delta compression, when you read the data, you have to read the base, read the delta, okay? So that means the read overhead is increased. So DCM only accepts if you are updating a file, DCM only accepts evicted delta from the file if the file is read code and write hard. Okay, so that is based on a clustering algorithm to identify read code, write hard files. So once again, you can check the paper for details. So now this is consistency and the recovery. Because our approach introduced base block and the deltas, so we must enforce new write ordering. So there are 2 rules here, and let me explain the first. So for the first rule, base block must be written before delta blocks. Written means persisted, flushed to storage, okay? And then before inode. That is to avoid dangling delta. So dangling delta is during recovery, we found a delta, but we cannot find the base. Okay, so that is an error. We can avoid this error by enforcing this write ordering. And this is another ordering. But anyway, based on this and based on the original recovery logic of F2FFs, we can guarantee the data consistency. Yeah, right. So we conducted experiment on a smartphone, and we compare with the original F2FS with regular data compression and our MedFS. So this is the main result. So as you can see, on average, we reduce the write traffic by more than 1/2, more than 50%. That is really, really considerable, right? And this can translate into a lifetime expansion by more than 100%. So the reason why delta compression works so well because we are focused on change, and the change is tiny, especially for mobile I/O. Okay, but for regular compression, its compression ratio depends on the data pattern. Okay, and the compression ratio, oftentimes it is not good. Okay. So this is user perceived latency. Let me speed up a little bit. So it improves the execution time for write-intensive scenarios. So this is I/O latency. So we reduce the write I/O latency by about 30%. And on the right-hand side, it is a little bit interesting that we also improve the read latency. Okay. That is because we significantly decrease the write I/O count. And this further alleviated the contention for the scheduler I/O queue. That is why read I/O latency is also improved. Okay, so this is my conclusion. Mobile applications, they generate a lot of tiny changes. Okay, so based on this, we propose using delta compression. So our proposal include DCI, DCM. We utilize the inline area, and if the inline area overflow, we store delta in regular blocks. Okay, so the reason why delta compression works well because the change is tiny, okay? In comparison to compression, sometimes it does not compress well because, for example, if this is a multimedia file, then it is not compressible, okay? So yeah, right, that's all. Thank you.